Yeah, I'm very happy that you two can meet each other. I think that Azra is a very inspirational person, and I really want to have a chance to hear her thoughts on cancer, and then ideally we can talk about some of her other interests as well. We'll spend some time on that.
Yeah, you definitely have a broad range of interests with literature and poetry and philosophy, so that's fascinating.
Yeah.
Um, all right, yeah, we can jump in. I'm definitely super excited to meet you, Dr. Raza, because I think your work is just laudable, mostly because, well, one, you actually treat patients with cancer. You also do research on cancer. You've obviously authored an amazing book called The First Cell. But your story with cancer is also deeply personal because you lost your husband to it, which is just devastating. Um, so I just want to start with a pretty basic question, which I think most people probably take for granted. But what, in your opinion, is cancer?
Thank you for having me, both of you. It's an honor to be on your podcast, and thank you for that kind introduction. Cancer, interestingly, is when some part of our body decides to rebel, because the body a, is a confederacy of cells, and it's the rebellion of one cell against the entire confederacy to simply be immortalized for itself. And that is what we call cancer, really.
And what do you think causes cancer? I know there are many different theories, many different causes of it potentially. What do you think causes it?
I would say stress. And let me explain why I say that. Um, because when you start looking at all cancers, whether they're liquid or solid in lymphoid tissue or brain tissue, there is a convergent evolution in that some things are common to every cancer, and that's how we define it. What are the two things common to every cancer is number one, that a cancer cell can ignore growth inhibitory signals. So it can continue to proliferate without paying any attention to what's trying to stop it. And number two, a cancer cell stops maturing. So an immature cell that proliferates or divides forever is cancer. And the question is, what causes it? Because it's starting in one cell. So people tend to think that, oh, there must be something wrong with the cell. But it could also be something wrong with the environment, the soil in which this seed is growing. Something goes wrong, which is forcing this cell to misbehave. What could that be? That's what I'm calling stress. And stress of something like an infection in the liver, for example. It's with a hepatitis B virus. The infection starts, the virus starts killing lots of cells. Immediately, the body responds with an inflammatory reaction. Immune cells start coming to that site of action to try and remove the debris, to eat up the dying cells. All this causes a lot of stress. Cells are now getting signals, fight or flight. Either you're going to develop a strategy to survive or you're going to die. And cells don't have time to think this out. They have to react instantly or they're going to die. So one of the strategies they develop under this stress is fusion. Two cells will fuse. That doubles their DNA, that doubles all their internal armament that they need to withstand the stress. So this fusion is a normal response to stress. And it happens between, let's say, if it's in the liver, two liver cells will fuse and now they can fight better. But once in a blue moon, a liver cell can fuse with a blood cell that had come to remove it or to take away the debris of this dying cell. When that happens, that heterotropic fusion between a tissue cell and a blood cell, that could cause all the problem. That's where it can begin. So then what causes cancer? Is it the seed? Is it the soil? Is it everything? Is it the immune system? I'm saying to you that it's all of this. It is an organic disease. It's a disease where the whole body is involved, because as soon as you involve the immune system, the blood, it's all over. So I'd like to continue our conversation as we go forward about discussing this particular aspect of response to stress, because obviously everyone knows that any organ which has chronic inflammation, whether it's the gut or it's the stomach or it's the liver or the uterus, anywhere there is chronic inflammation, cancer is more likely to arise. And it is because of this stress-caused fusion.
Interesting. Do you see this fusion in all types of cancer?
Every single liquid or solid cancer that has been examined have found these kinds of hybrid cells, meaning the same cell expressing a blood marker and a tissue marker. We call it a cancer hybrid cell, CHC. So, for example, 11 years ago, I started to filter the blood of my patients, filter them in a device so that the blood cells will go through, but anything larger than blood cells will get trapped on the filter. What was I trying to do? Because I study and treat pre-leukemia and follow these patients as they develop acute leukemia, I was trying to find the first leukemia cell. And I did find leukemia cells on the filters, which are larger than normal cells. And that was my idea, that a coffee filter-like technology should work. But what was shocking was when I started to find these giant cells. So if a blood cell is 15 microns and a blast is, let's say, 20 microns, these are 100, 200, 300 micron large cells with lots of nuclei inside. And this polyploid giant cancer cell, PGCC, led us to start looking everywhere about what's happening in other cancers. So we were the first to find these in liquid cancers through filtration of blood, which I was doing for other reasons. But solid cancers have been studied through liquid biopsies. So let's say there's a tumor in the pancreas or lungs or the colon. These cells can be found in the blood. Why haven't other people found it? Because they're so rare. In the primary tumor, we see once in a while, as you're going through under the microscope sections of tumors, you'll see a very large cell, and pathologists always note it, and they always say, oh, this is a dying cell, or it's a macrophage, or they just say things like that because they're so rare. But now that we've developed technology to look at gazillions of cells circulating in the blood through liquid biopsies and filtration technology, we have started to find these. So yes, and my group has done filtration to find in hundreds of leukemia patients. Then we looked at single cell RNA-seq data from colon cancer and breast cancer patients, hundreds of them, and showed cancer hybrid cells in every single tumor. And finally, my company, the First Cell Therapeutics, which is trying to develop a bispecific antibody to target and take out these cells, because the two antigens make it unique, right? A blood antigen and a tissue antigen is only present on such a hybrid cell. No other cell in the body should have these two. So we can take it out with the bispecific antibody. So through the company, we have now studied lots of different types of solid cancers: thyroid, uterus, breast, liver, everything that comes through. And we are finding these everywhere. They're rare, but they're there.
Is it always the case that when these stress cells fuse with another type of cell, it ends up being cancerous, or in some cases, it might not actually end up, you might not end up with cancer?
When we look at single cell RNA-seq data and say to the algorithm simply says, any cell that's expressing these two markers, tell us if they're there or not. Then the way we look at it is we look at the actual tumor, then the normal area surrounding the tumor. We look at cells there, and then cells from the same organ of someone completely normal who doesn't have cancer at all. So you have two controls. One is a healthy person, and the other is normal surrounding tissue around a tumor. And then we have the tumor cells. The hybrid cells are more in number within the malignant cancers, but occasionally we have seen it in the surrounding area and occasionally in healthy people. In healthy individuals, it's usually because of some infection they're having. In surrounding tissue, they're there, but very, very much fewer even than in the malignant area, except we looked at their gene expression profile because we're looking at transcriptomics data on a single cell basis. So we look to see, is there a difference between hybrid cells found in the malignant area versus normal areas? And it's an entirely different milieu. It's shockingly different. Number one, you have tons of telomerase being expressed in the malignant hybrid cells and 0.00 in the hybrid cells found in normal areas. Number two, the transcriptomic profile, interestingly, is totally inflammatory in the malignant hybrid cells, but not in the normal. So we can occasionally find these cells in normals, but they're very different.
Going back to something we were talking about earlier, which is what is cancer, and it's some cells rebelling against the other collective of cells. Why do you think, because of this stress-induced environment, why do you think the cells choose to respond in this manner of just being immortal and proliferating and constantly growing versus normal cells? They're not immortal. Why do you think that's the case?
Yeah, very good question. And that basically is asking the question, why don't normal cells become immortal? Or how do normal cells die that cancer cells have overcome that step? Thing is, there may be 1,000 different strategies that are being followed by these cells. I'm just picking up on one, which is fusion. I don't know how many others there are which are successful and working all the time. This is why cancer is rare. And science is forever a self-correcting enterprise. We never say anything dogmatically because we know tomorrow we may be proved wrong. And we have to be prepared to accept it because we're not religious leaders, we are scientists. The difference between science and religion, I think Carl Sagan described it the best. He said that religion is all about preserving the exact text that came, even if it was thousands of years ago. You have to preserve everything. Science is constantly a changing expedition. You have to keep correcting. And I feel that there are tons of strategies cells follow under stress. One of them is this, and one of them seems to be present here. Why am I so interested in it? Because independent investigators have been noticing that when, for example, you remove every microscopic sign of a cancer, solid cancer, for example, then recurrence or relapse begins first with the appearance of these giant cells. Or people have shown now in thousands of cases that, let's say, you remove somebody's lung cancer, and after all the treatment, surgery followed by radiation and chemo, you now post-therapy perform a liquid biopsy. If you find a single giant cell after this treatment, relapse is imminent. And if you don't find any giant cells, there's a straight line of survival, followed for several years now. These studies have been going on for over 10 years, but no one wants to think about them because everyone's so obsessed with generics, one gene, one magic bullet is going to cure cancer. We can't think beyond that. Biology has taken a back seat to the microbiologists.
So in terms of being diagnostic, you could, in theory, just test whether there are some of these large cells and figure out a patient's risk for relapse, right?
I think we have done better than that. Henry Ford in 1909 said, if I had asked my customers what they want, they would have said a faster horse. I gave them an automobile instead. So what I'm going to show you as our solution to this problem is a jet plane in the days of horse carriages. We are so far ahead of the game. This is the cure for cancer I'm holding in my hand. It's a syringe and a needle. And the cure for cancer is not in the syringe, some medication. It is in the needle. What is in the needle? In the needle is a coronary stent. You know, stents that are put in to open heart vessels. Millions of people are walking around with these coronary stents, and stents are put in the bile duct, in kidneys, in the heart, everywhere stents can be put. Well, we have a stent inside this needle, which has electronic circuitry that is shown here. I've spread it out. This is the work of biomedical engineers at Columbia University, Sam Sia and Ken Shepard. I've been working with them for 10 years on this device. The electronics is such that we can inject this stent, it's an implantable device, into one of the large blood vessels in your arm. And this stent will go and sit there forever. It can stay from birth to death, we think. And then it creates an electrical current so that anything that passes through that electrical current will cause impedance. And by picking up electrochemical impedance spectroscopy, you can tell a small cell from a large cell. So the first thing we can do is anytime a cell larger than an expected normal blood cell passes through this stent in your arm, it's going to immediately send a signal. And there is a chip that is built in here that will record it. And it's going to your cloud above your head in the data cloud. It's all being recorded and continuously AI monitored. So the idea is here that we can program the stent, Asta, that if you see a cell bigger than this size, electrocute it.
Wow, that's fascinating. I have so many questions. But Mike, this seems like this ties into your work with bioelectrics as well, because you've been looking at the bioelectrics of cancer. So I'm curious, what are your thoughts on this?
Yeah, I love it. Super creative and interesting. Just one question I had on the kind of on the basics of it. What do you think for this fusion? Do you think that the ability to do this or the tendency for cells to do this under stress, do you think this is an innovation of multicellular body plans, or do you think this is something that unicellular organisms would do under stress anyway? Like, how ancient do you think this is?
We see this all the time. I mean, look, in fungi, you see unicellular fungi that actually start sticking together and forming groups and colonies, and they make literally termite-like branches out like that. So no, it is common to our most primitive life forms. What do you think, Michael?
Yeah, I mean, as you know, we've discussed before. I think thinking about how the system responds to stress is critical, absolutely critical. And I think your focus outside of the kind of the genetic causes are again super important. What we study is the disconnection of cells by stress, by a number of other mechanisms that induces them to disconnect from the rest of the tissue. At that point, so my story about this is that larger group cell collectives can have very large cognitive light cones, meaning that their goals are large. They maintain and they build organs and all this. And then as stress causes them progressively to disconnect electrically, then all of their sort of goal states shrink to very small things: survival, migration, proliferation, ancient unicellular kinds of things. And so it's very interesting to me that during that process, as they are leaving the large collective of which they are part, which makes sense. I've been part of this. It was great, but now life is not so good. The stress, for some reason, I'm leaving this organization. I'm out of here. And so, but yet they're interested in fusing with something else on their scale. And it's almost like like an attempt to reboot their multicellularity. They're just gonna, they'll merge with something else and see how life is that way.
Absolutely. And I wanted to add to it that, look, I think of it like a somatic cell pregnancy. because that literally, when these two weird cells, completely different lineages, fuse their genome, what emerges is something that has thrown its program back, its differentiation program back to the zygote level. And that's where it gets stuck. So it's now immortal because it has the zygotic ability to continue to form from one cell a huge adult eventually. But also, on the other hand, it has kind of become immortal because it has continuous power to proliferate. And it's so interesting to just even think about what electronics are playing, what role here. And that's why, Michael, I've always been interested in trying to develop a common program with you, because I think that if we combine our strengths and have implantable device, plus, this implantable device we call it, by the way, the biomedical engineers who are Sam Sia and Ken Shepard have named it the Stantinel. And I love that name. It's a stent and sentinel also. So it can also detect biomarkers like pieces of protein, RNA, DNA by this very tiny molecular signaling that can be detected. So this is all being done in vitro already, so that when we get the device inserted, all this is ready. And the last thing I want to say is that, Michael, you know that I started my career in this country when I was 24. I had come here and wanted to start my residency in medicine, but I arrived here in January, and my residency wasn't going to begin until July. So I panicked. I thought in these 6 months, somebody is going to cure cancer and I'm going to be left behind. So I just showed up at Roswell Park Cancer Center, where I was in Buffalo, and said, please make me do anything. I'm ready to start. So they put me in, they had a fellowship available for 6 months. They gave me in pediatric oncology. So I began in pediatric oncology. But within 3 months, they sent me off, not because I was doing something wrong, but because I was crying the whole time. Honestly, I just can't sit on babies and 2-year-olds and push bone marrow needles into them and spinal taps and all the horrible things we used to do to them. When I got to the adult service, as a result of these crying fits, they sent me off. The first thing I noticed was that the same 3 drugs we were using successfully to cure acute lymphoblastic leukemia in children had no effect in adults. The disease was exactly the same. So what was different? Obviously, the rest of the cells in a 2-year-old are nascent virgin cells, whereas in a 70-year-old, every other cell in the body has received 1,000 cuts. So it's going to metabolize the same drugs very differently than a 2-year-old's body. So basically, we could even have the best curative treatments, but they won't work. They'll work in one and not in another situation. Secondly, I realized, guys, that even if a littler version of ourselves cannot serve as a model for the adult self, then how are we using animal models to try and develop drugs or try to understand cancer when that animal does not get that cancer spontaneously? We produce something in it, we immunocompromise the mouse and then give it some cancer cells and claim, oh, it has developed lung cancer. Oh, this is, I mean, how this occurred to me when I was in my 20s, that you can't use any model to study. You have to use human cells. And also what Norbert Wiener said, the god of cybernetics at Harvard, he said that the best model for a cat is another cat, preferably the same one. Which means the only way to really look for a cure is to personalize. What we are finding in you, Asta, or in Michael may not work for me because my lifestyle is completely different than yours. I eat masalas and chicken tikkas all the time. You are surviving on hot dogs and hamburgers, which are bland and tasteless. But anyway, the idea is that you, in order to personalize, that means you have to go to the individual. But then, second, cancer is a silent killer. It doesn't announce its appearance. It can be stage 4 before you detect it. And number 2, no age is immune from cancer. So then ultimately you need a technology which can start at birth, continue till death, which continuously monitors for wellness to illness transition. That's what you need. And this to me is so logical. But I'm treated as the pariah in the field for saying this. I'm the one who's treated as if I've written the satanic verses of medicine.
I mean, for what it's worth, it makes a lot of sense to me. If you can monitor it from the start and then nip it in the bud just when it's beginning to form, that's obviously the best way instead of letting it progress. But in terms of it's personal to everyone, do you think the stantinil could be applied universally to everyone, or would that also have to be personalized in many ways?
The same stantinil, like the same coronary stent, works for everyone. Asta, I come from a third world country. I come from Pakistan. The entire budget of Pakistan, which is a country of 230 million people, is $34 billion. Whereas last year in America, just phase 1 clinical trials of cancer, 86.7% of which completely bombed, cost $60 billion. $60 billion thrown away in phase 1 trials. Why? Because the preclinical testing platforms were all these artificial models on the basis of which drugs were assessed as being extremely powerful and curative and brought to the bedside. And we haven't learned this lesson that 95% of these things are failing today. And the 5% that succeed are not curative. For a fraction of 20% patients, they can improve survival. I'm talking about advanced cancer. Those that appear in the early stage 1 or 2 can still be treated with those Paleolithic therapies of slash, poison, and burn. Nobody should be living through any of that caveman stuff. We should have patient-centric, compassionate solutions, and that only means revolutionize early detection, for God's sake. That's where we should be focusing. Instead, we constantly focus on the last cell and developing more and more toxic, more and more elaborate therapies that can be given to 10 patients in America, and the rest of the world can go to hell. So I'm telling you that this is the way to democratize medicine. This is the way to take it to populations of underserved communities in this country who have no access to screening measures and personalized treatments. I think this is the only way.
Yeah, the personalized aspect I think is really critical, and we're starting to look at, we make these anthrobots out of specific patient patient samples. We're starting to look at how these things interact with cancer cells, for example, and how they're going to behave under stress, how they're going to interact with. I mean, we can think about some very specific things based on what you were saying today. But I think these kinds of personalized models are going to be very important. Yeah.
But what Asta asked is this stent going to work for everyone, or do you have to personalize it? I'm saying you don't have to personalize a stent, but the data that you collect and how you're going to deal with the problem that it poses, that's got to be personalized, of course. And that's where, Michael, what you're saying is spot on. We need help of people like you who are in a completely different discipline, who can think about it very differently than I'm thinking, or the biomedical engineers are thinking about.
Yeah. We
So
also,
on this,
please
go ahead, Mike.
No, you go.
No, go ahead. No, I was just going to ask on the stantinil point. I think it would be amazing for people if you could just elaborate on how it would work in terms of detection. I know you mentioned it's the electrical current of the large cell versus small cell would be different, but sort of just a little more details on how it would work, I think would be amazing.
First of all, I'm not a biomedical engineer, so I don't want to go into any kind of detail, but roughly speaking, that lay people can understand is that if there is an electrical field that is created, then anything that is passing through that electrical field will cause disturbance of the field. And if the thing that's passing through is small, the signal it gives is small. If it's large, it's going to be a large signal. And that's all we are picking up. But that's about the size of the cells. However, for the molecular kind of screening, which comes with because we don't, let's say that I put this stent in my arm and it detects a first cell. It will relay the signal to the chip that is on it, and that signal will be read and relayed immediately to the cloud where the data are being gathered, will be analyzed by AI, and some kind of a warning is sent on my iPhone through an app to say, look, some trouble is brewing, and then you go in and look, okay, it's detecting. So this little stent can scrutinize and monitor and analyze the entire 5 liters of blood in an adult every 18 days. So how different is it than doing a periodic 10 cc's of blood for detecting some biomarker once a year? This thing every 18 days is going through all your entire 5 liters of blood. So let's say it detects that there are giant cells. What does it mean for me? What should be as a patient now? What should I do? Should I go in and ask for a bone marrow transplant? What should be done with this cell? Well, I don't think we should rely on any one parameter to make these kinds of decisions. I think a stage is set, first of all, for this first cell to arise. So if we detect the first cell, we should immediately think, okay, what is the stage that is being set? Is there some inflammation going on? How can we detect these markers? So this is why we go to the biomarker detection. But the thing is that I realized the importance of the environment, microenvironment, way back 40 plus years ago. And I started to save samples on my patients, not just blood, serum, plasma, saliva, bone marrow aspirate, but I started freezing in DMSO bone marrow biopsies, which are completely intact geographically. You see, where everything is in place. It's not like you're suctioning something and mixing up oranges and apples. That is all preserved. I have all these going back to 1984, 60,000 samples from thousands of patients longitudinally obtained in my tissue repository. No, not one cell comes from another oncologist. And what's more, I have taken care of every single patient with my own hands. Every vial means something to me. This is not some game for me, because I see 30 to 40 cancer patients a week. I'm answerable to them, and I'm giving them the same horrid news for 40 plus years. It's shameful. So that's one tissue repository that we can go to, do multi-omics, find out what biomarkers were associated when this cell appeared. First, right? Second, I'm studying pre-leukemia and trying to see what biomarkers and what cells change when acute leukemia occurs. But what about solid tumors? So I said, okay, we should be studying people who are at risk of getting a solid tumor, start following them when they're at risk until they develop it, to see, can we catch the first cell? Can we catch what I call the first cell stage of cancer, which is very different than stage 1. This precedes stage 1 sometimes by years, where the inflammatory environment is being produced. So who's at risk of cancer? The highest risk is in cancer survivors. Now, people listening to this podcast, any of you who have had cancer or who have family with cancer or some loved one who is a cancer survivor, don't get anxious. Because the individual risk for a cancer survivor to develop a new second cancer, not recurrence, a new second cancer is only 13% higher than normal. But if you look at the population as a whole that is getting cancer, then it's 20% of all new cancers in the US occur in a cancer survivor. So I started to collect their samples. And I have a whole repository of cancer survivor samples in which now so many have developed new cancers. Some have developed recurrence. Now I have all this right now trapped on filters, but future it will be trapped and sent here. So I know this science sounds like science fiction, but then what Michael does also sounds like science fiction. People don't believe me, Michael. They think that it's a pie in the sky and I'm just imagining these things. That is not true.
Yeah. Well, I mean, science fiction just means you have a slow Gantt chart. People who think this is science fiction. I mean, it's time. But I think it's really important that everybody hear what you're saying as somebody who actually takes care of these patients, especially the pediatric patients, because I'm not even a clinician, and I receive all kinds of emails saying, why do you do this research, with the frogs and the worms, and this is you shouldn't do these things. It's too much. It's too far. It's too, we shouldn't be doing these things. It's scary. It's whatever. And I just it blows my mind, because anybody with the slightest exposure to this the amazing patient populations that are out there, the suffering that's out there is just it's incredible. And there's a huge segment of people, I guess the healthy people, I don't know, that are just, they're not seeing it. They don't understand that this is what's at stake. That every time you either suppress or actually fail to support the efforts to understand what's going on and help people, you are, I think you're complicit in this suffering. I mean, we have to get this stuff under control, and I hope everybody's hearing what you're saying, what it's like to do this on a day in and day out basis, to tell people what their experience is going to be. I mean, I don't have the words for it.
It's heartbreaking.
Yeah.
I can't, my book is full of just patient stories, because I'm looking at everything to do with cancer through the prism of human anguish. What is it we are doing to the patient, to the families, the psychic violations we are visiting on them? It's just not for one individual. I'll give you one example, Michael. When my own husband died, my daughter was very little. First, he was diagnosed when she was only 4. So she was very tiny, poor thing. But she grew up the next 4 years, practically 5 years. So she was 8 when he died. And 3-4 weeks after he died, she got a very bad flu. So, of course, everything is being given to her. Her asthma acted up, etc. But 1 week later, she was getting better. And then I was sitting in my living room one morning, and she came out of a room crying inconsolably. As a mother, my heart sank that she's feeling much worse. Something's happened. I said, what is it, Sherzad? And she couldn't answer. When she controlled herself, this is what she said. She said, no, Mom, I feel fine now. But now I know how horrible it is to feel that sick and how good it is to feel better. And my dad never got better. This is the sensitivity of an 8-year-old who's empathizing with her father who never got better. What kind of society are we living in, that we are tolerating the suffering of millions of people and giving ourselves gold medals constantly for game-changing therapies? They're all technologies, for God's sake. They're doing very little to help our patients.
Well, speaking of that, what is your current assessment as far as, from where we were, I don't know, 50 years ago? I mean, you pick a time, but how are we actually doing? Is there anything that actually is reasonable right now? Some sector of the patients that are actually getting help, and what does that look like in general?
Yeah, I mean, of course, there are subgroups, little islands of responses, but they are so little. I'll give you an example. Everyone talks about CAR T therapies, the immune therapy where you and bioengineers immune cells from the same individual to go and target their cancers. Everybody is talking about them. Let me just give you the statistics on that. Last 10 years, 27,000 people received this treatment in 10 years. In 10 years, what was the incidence of actual cancers? 2 million, 20 million, 2 million a year. So nearly 20 million cancers. So first of all, out of 20 million in 10 years, you have treated 27,000. How many patients, what percentage is it good for? Okay, what is the treatment cost? Minimum $1 million for each patient. Okay, what about, that's the financial toxicity. What about physical toxicity? Because that CAR T cannot make a difference between what is a normal B lymphocyte versus a malignant B lymphocyte. So it's going to kill every B lymphocyte in the patient's body. And now, how do you replace those immunoglobulins? For the rest of their lives, they have to get immunoglobulin replacements. And what is the outcome of all this horrible toxicities? Physical toxicities are terrible. Go and see some people's brains just liquidated in the presence of these CAR Ts. What is the outcome? The median survival for these 27,000 patients is 14 months. Meaning half of those people are dead within 14 months. Yes, there is a longer tail going out. The second half of the median has a longer tail. But so you are developing a treatment that is costing this country to come on the verge of a financial collapse in the health sector. You're developing that kind of treatment for a small percentage of patients, which is not too much better than chemotherapy for at least half of them, because they're dead within 14 months, like they would be with any other treatment. So I just gave you this extreme example because as you asked me, well, some people must be doing better. Yeah, there are cancers. Lymphomas have like 10 other triads, or malignant melanoma, lots of good antibodies, immune therapies. What about multiple myeloma at one time? It killed, median survival was 5 years. Today, so many people live median of 10 years, if not longer, with multiple treatments that have been developed. But taken together, these are very few cancer patients. The vast majority of brain cancers, lung cancers, GI cancers, bone marrow cancers. I mean, the more common cancers, you ask me, what is the difference? I say not 50 years ago, 100 years ago. If somebody presented with a glioblastoma stage 4 100 years ago, the outcome is no different today for a glioblastoma stage 4 than it was 100 years ago. What about pancreatic stage 4? No different. Take any of these cancers. Once it's advanced, all bets are off. For my cancer that I've been treating, acute myeloid leukemia, you won't believe this. In 1977, when I started, we were treating the disease with 2 drugs, popularly called 7 and 3, because 7 days of one, 3 days of another. Today, in 2025, same 2 drugs, 7 and 3. In 1977, what was the survival? 5-year survival was 26% in 1977. Today, it's 28%. And that 2% increase is not because we have better drugs, because we have better supportive therapy, better antibiotics, better antifungals. This is the state of affairs, Michael.
This brings me to a more fundamental question. Why do you think we haven't made that much progress?
I think about this. It's on my 3 a.m. agenda. I stay awake thinking about why is it that other people are just blind? And I'll tell you, there's a complex battery of reasons, but one of the most important reasons is that as doctors, we enter a profession to treat disease and help our patients, right? We never think of prevention. So the entire focus is always on treatment. So the first problem is doctors themselves. Second problem is that doctors who are seeing patients don't do research, and researchers who are studying cancer in their labs don't see patients. This is a crazy kind of thing. It should never happen like this. And there is no crosstalk between them. They hate each other most of the time. Number three, the way the system has evolved. The whole field has been hijacked by money trails. So if the government agencies that put out grant requests will ask for grant requests in certain areas. And if you don't apply in that area, you get no funding. So you have to channel yourselves, even if you're thinking differently, in the end, you'll have to do those things on mice. For example, in 40 plus years that I've had my tissue repository, nobody supports it. There's no mechanism to support this. So I hold fundraisers. Who helps me the most is my patients. They try to give me personal money. I say, no, I don't need, please give to my tissue repository. So they give us support. This is how I'm running the tissue repository and groveling and begging in front of everybody, because the whole system is that academics apply for these government grants. They use models that are so abnormal. They develop these things, and then they have to hand them to industry to develop it further. And industry's stated reason for existence is to make money for their shareholders. So they're not going to worry about what patients are dying or what we are doing. Their thing is, how much money can we make out of it? At least they're honest about it. But think of the academics who are handing these horrible targets to the industry to develop. So now you tell me who's responsible. I don't know whether it's doctors or PhD researchers or government agencies or all of us in collusion.
Well, I think you're at the epicenter of like just state of the art cell biology, bioengineering, and the clinical side of things. So I think what you're doing is incredibly important, and like that's the synthesis of those three branches, as you said, is not common. It's not common that people do this, and I think it's a very powerful set of new ideas. So.
But this is why I've become an old woman and constantly disregarded, disrespected, and ignored constantly. So why? Because nobody else is doing what I'm doing. By the way, I wanted to also point out, full disclosure, that around this stantinil, the two biomedical engineers, myself and my scientific colleague, we have made a company, because that's the only way people are even willing to give money to invest in something. And of course, Columbia, because we are an academic center, Columbia owns most of the equity. They own the intellectual property rights, etc. I wanted to tell you, Michael, that, okay, we made a company and we said, okay, if we get $6 million, what is $6 million? It's nothing. $6 million, we promise you that we will have this device plus the tissue repositories, cancer survivors, and our own, examined by multiomics to deliver the biomarkers we need, plus the cells we already know, plus the stantinil in 18 months, ready for discussion with FDA for IDE, investigational device exemption and implantation. We shouldn't have a problem because this has been implanted. This is getting implanted all the time, stents. So it's not really different. So, and we are not doing anything with it except to detect certain things. So it shouldn't be a problem with the FDA. But we are ready to deliver in 18 months all of this for $6 million. And the last big investor I had a meeting with, you guys won't believe what I was told. Guy said, yes, Dr. Raza, we believe that you are a credible person. You've been interested in this area and you've done all this. Yes. As I pointed out, $50 million have gone into developing this device. And what I have in the tissue repository, you can't even put a dollar figure on its value. And so we have all this. He goes, yeah, I understand all that. And you are likely going to succeed and get this device in. But in order for me to invest with you, you have to do a study of doctors' behaviors, that once you have this approved and ready for implantation, that doctors will actually do this. So please do a study first to show me that you can change their behavior. And then I'll think about investing. Oh my God, this is what I'm dealing with. I asked him, do you guys ask this question when you are investing in drugs developed in mice? What kind of accountability is there for others that is there for me? I don't know. Is it because I'm colored? I have an accent? What is it? What am I saying that's wrong? 11 years ago, I gave a TED talk saying all of this, Michael. My first slide on the TED talk was a picture of a mouse. And I said, this is the real elephant in the room. What effect have I had on the world? Nothing. And patients are dying. That's the horrible thing.
Well, I think the good thing about something like the stantinil is that consumers will ask for it because they'll want early detection and prevention. So if you can just go even the private consumer route, I think that's probably going to be very high demand for that.
Very good point.
I know we've touched on this a bit. I'm sure people have some context, but it would be good if you could just clarify again, what do you mean by the first cell stage of cancer? And you said this is very different from stage 1 cancer. So what is the first cell stage of cancer?
What we are calling the first cell stage is when we can detect the biomarkers, like the pieces of protein, DNA, RNA that are associated with whatever chronic inflammation is going on, and setting up the stage, and then the appearance of the first cell, which is the appearance of these hybrid cells. If these two are together, we think this is the first cell stage of cancer. And at this point, Asta, reversing with even lifestyle changes could work. Or even drugs like metformin or Ozempic could work. Just finding it and reversing inflammation is much easier than trying to deal with that end stage monstrosity that is impossible to control. And by the way, this stent will be useful eventually and very quickly, not for just cancer, but for early detection of all chronic diseases like dementia, anything, you name it, it can pick up the wellness to illness transition all the time. And yet, look at the difficulty I'm having raising $6 million. It drives me nuts.
I'm curious if, obviously, the stent has been used in the past, like you said, and it sounds like the novel technologies and the actual detection and figuring out what's a cancer cell and the biomarkers. But why has this been tried before? And if not, why hasn't this been tried before? Because it seems like such an important thing to work on, to have early detection for all sorts of diseases right from the start.
This is the question I keep asking. Why is no one looking at the inception of cancer? Why is everyone trying to develop treatment of established cancers? Because the mentality of doctors is to treat. This is how we grew up being doctors. We don't think of prevention or early detection at all. People who have thought of early detection, they've tried periodic liquid biopsies, and they've all had their problems. Because the ultimate solution is what I said, it has to be continuous detection. And it has to involve more than one thing, not just cell-free DNA looked at for methylation patterns. No, you have to combine multi-omics to come up with the right signatures that are unbeatable, that are really very strong and prove the presence of abnormality. I think why haven't people done it? Because they're focused on the last cell. If only we would focus on the first cell, we would be making such rapid progress. Because think of all the intellectual assets that are being lost right now in those useless studies. Think if we reverse them and forget about the money, it's the intellectual input that's so badly needed. And no one has tried this concept in cancer, absolutely. But there are stents like this for other things, like CardioMEM. Exactly the same stent we are using. Measures pulmonary pressure. And that's very important to measure. That has the same electronic circuit as here, okay? So these things have been implanted. That was approved and eventually bought by Abbott for $427 million. So these are working constant. 20,000 people a year have that stent placed in them. So it's not cancer stent hasn't been developed or placed, but others have.
I guess maybe the last thing, do you have anything to say for people? What should, if somebody has been given a diagnosis at this point, what should their first step be to educate themselves on what is actually useful, what is worth doing, how to navigate this thing? What should people do when they get this scary diagnosis? What do you recommend people to do?
Listen, I deal with this all the time, Michael.
Mm-hmm.
The only good news we can give our patients when we are diagnosing cancer is to say it was diagnosed early. That's the only good news because that's at a curative stage. So the first thing when somebody is diagnosed is to figure out where their disease is, whether it's curable or not. And if it's curable, then what are the strategies that would be followed? Is there just surgery that will remove it, or chemo, or radiation, or immune therapy, or combination of all? What steps? And if the patients can't do so much because there's so much psychic trauma that goes with it that your mind becomes foggy. You're getting constant information from doctors and trying to manage appointments, and I mean everything. There's a big difference between the kingdom of the living and the kingdom of the dead, where you get moved with that diagnosis until you come out of it. And it's a very confusing and complex situation. So that's why cancer involved not just the individual patient, but the family and even the community is involved. Half my patients are coming with accessorides because they are on social security and they just can't travel. So accessoride and things, these services, so community services bring, church services bring them over. And I think it's so important for patients. I mean, obviously, the wealthy ones with lots of resources available to them can have all this at the tip of their fingers. But for people who are not so fortunate as having that much money, there is the internet. There are young people around you. If you're not at home with using these electronic devices, get as much information as you can. But then the most important thing I'd say, Michael, is find a doctor that you think is communicating with you well and is sympathetic enough to not just trying to cure you, but actually is concerned about healing you. Because the violations that are going to be visited on your body and your mind are so profound that you do need some partner in this journey who you feel comfortable with. I think that's an important thing. And that's where Emily Dickinson says beautifully, surgeons must be very careful when they test their knife. For underneath their fine incisions rests the culprit, life. In other words, a surgeon can use a knife to remove a wart or a tumor. But the problem is underneath their fine incision rests the culprit, life, which is a far more inclusive and complex situation than just curing the disease. You have to heal the person.
And I think at some point maybe we can do another session at some point. I'd love to hear your thoughts on the prevention side and the stress and the link to psychology and to other aspects of life that might sort of go beyond the traditional thoughts of chemical stresses and things like this. Thank you so much for today. I think this is just super important for people to hear, and thank you for your amazing work. I love your approach. The technology is very promising. Thank you for that.
Thank you so much. Likewise, I'm looking forward to hopefully you curing cancer.
Through early detection.